So now let's go ahead and code it up. I want to fire up MATLAB. I'm going to actually take a look at the editor, go into the editor. Looks like old stuff. Try a new thing here. So I want to write my phi calculating function first. Function. Phi val is what I'm going to call my return variable, and my function name just phi. And it's a function of an array R, which contains 3 values representing the coordinates of the point at which I'm calculating phi. End the function, and then the body of it goes in here, tabbed over. So let's see what I had in mind there. I got to initialize some values. So let's get going with that. That was A equals I think it was 0, 0, 0.005. And K equals 8.99 times 10 to the 9th. And Q equals 50 nanocoulombs. Alright, then what? RP is the norm. So I'm getting the two distances that point P is away from the charged particle. The distance that it is from the positively charged particle, RP, is equal to norm of R minus, so it's up to the user to recognize, hey, this has got to be a 3-element array that they got to pass to this function, and inside I'm just treating it as if it's a 3-element array. R minus A. And then the distance from the negatively charged particle is the norm, or the magnitude of R plus A. And yeah, the two charged particles were supposed to be 1 millimeter apart. No, a centimeter apart. So each of them half a centimeter away from the origin. Yeah, half a centimeter below, half a centimeter above. Thinking of plus C as upward. Alright, let's get back to the editor here. So then phi is equal to K times Q times 1 over RP, and then minus, because the charge associated with the second term is actually minus Q, 1/RM. That's actually phi val. So I have assigned the answer to my return variable phi val. So I think this one's done. Go ahead and save that. Save. They want me to save it as phi.m, which is just what I should save it as. So I'm supposed to save it as a .m file having the same name as the function phi.m. Alright, then I got to write the main function evec, that's what I'm going to call my return variable for this one, equals just e of r, where r is an array. R is equal to the array containing the three values x, y, z, which are the coordinates of the point where I want to find the electric field in this different function. And let's see what my plan was on that. I'm going to initialize the step size. Sure. So init s is equal to .1, and then define half a dx. I think I'll write it out as half dx in the code. I don't think that'll be much extra work, and then it'll be more clear. Half dx, or dx by 2. Alright, I think I'm ready to start programming. So s step. I go step equals 0.001. That's millimeters, and I'll go half dx. Yeah, I'll leave that underscore there to separate the two, so it's easier to read. And that's equal to step slash 2, comma 0, comma 0. Then I don't know if this is going to be faster or slower, but I'm going to copy that, change that to a y, that to a z. Try moving these guys around. So this becomes 0, comma step over 2, comma 0, and this 0, comma 0, comma step over 2, step size, step over 2, half step, yeah. And alright, then ex equals phi, function I wrote, evaluated at the vector r plus. Yeah, I need a negative sign all the way out front. R plus half dx minus phi of r minus half dx, all divided by the step. I think that'll do it. So I recognize I could distribute that minus sign and make it look a little bit easier, but I think it makes it more obvious. This is delta phi, and so I got negative the change in phi divided by the step. So it makes it a little more self-documenting by not distributing that minus sign to make the equation look a little simpler. So let's try, see how well I can do with a copy and edit. Z and Z. I think that looks good. And evec, that's my return variable up here, equals the array ex comma ey comma ez. So I'm going to save that. As e.m, and I guess I should try testing these guys out a little bit, just to at least see if they work. Let's see where I am there. So I had phi. Let's make it of rvec, and it returns a value and nothing else. And then that seems big. So let's take a look at that. It seems too big to me. Yeah, Q is supposed to be I was only off by a billion, by a factor of a billion. Right? Billion, 10 to the minus 9th. So billion, 10 to the 18th. It was, I think. So let's save that and try running it again. So that many volts, that makes more sense for the charges that we got. And then E of rvec. And let's go evec equals E of rvec. So I'm trying to assign the output, whatever this one returns, I want to assign it to this. So output argument not assigned, and I thought it was assigned. So might have to do a little debugging here. Misspelled vec. Control S. Let's try that again. Alright. There we go. Let's see if I can make a little bit of sense. We got a positively charged particle on the z-axis just above the origin, and the same amount of charge but negative charge just below it. So in this picture, see if there's anything we can check. So due to those two charged particles, let's see where my here's the picture of it. So right up here on the z-axis, I would say we're closer to the positively charged particle, and so if I'm right on the z-axis, I would expect E to be in the plus z direction. Let's Let's see if that's what we find. If this thing is working. E of evec equals, so that I get the output, so that it shows the output here. I'm going to go evec equals, and then E of, and then I'm going to go, let's see, the two charged particles are a centimeter apart. So let's make it pretty strong. I'll go 2 centimeters. Oh, I want it to be on the z-axis, so 0, 0, 0.02. And so, pretty close to the charged particles. Before I was talking meters away there. With remember my RVEC was 1, 2, 3, and now I'm real close to it. So I'm getting a big, strong electric field, and it is. EX is 0, EY is 0, and EZ is this 1.28 times 10 to the 6. So that checks. I want to check one more thing, make sure I got those the right distance apart. So that would be in phi, and I got 0.5, which would be 0.5 centimeters above. There's 1.5 centimeters above the origin and 1.5 centimeters below, so that does put them a centimeter apart. And yeah, and then I was checking it out, 2 centimeters above the origin. Let's try right at the origin. I think we got room in there that it's not going to blow up on us. So let's try 0, 0, 0. So what I'm expecting, if the function is working, at the origin, the electric field due to the positive charge will be downward at the origin, strictly along the z-axis, and due to the negatively charged particle, it will also be downward. So we're going to get a really strong electric field in the minus z direction. Let's try that. So yeah, before it was 10 to the 6 for a couple of centimeters up from the origin. Now at the origin, half a centimeter down below the positively charged particle and half a centimeter above, we get a greater magnitude and negative directions. So that checks. At a point on the x-axis, that's at a point over here, the downward component of this is going to cancel the upward component of that. So I would expect no. The downwards add up. It's the left and the right that cancel. Like this, imagine a charged particle right here. This one would be pushing it down that way just as hard as this one is pulling it this way, because they're both the same distance from this point on the x-axis. And so I would expect the 0x component, there would be a negative z component, and neither of the two vectors have any component in the y direction. So 0, 0, minus something for a point on the x-axis. So let's check that out. I think the origin is on the x-axis, so in a sense we did check it out, but let's make sure. So if I go, and the biggest part is canceling out. So if I go with like 2 centimeters here, 0.02, then I expect it to be weaker than this one up here. that was 2 centimeters on the z-axis. So this is negative. I'm at 10 to the 5th, which is smaller than the times 10 to the 6th when I was on the z-axis. And then along the y-axis, I should get, again, strictly minus z. So if I went 0.02 there, and just 0 here, same exact thing, yeah, I should expect the same exact value. Is there any place where I would expect the electric field to be 0? And other than infinity, I would say no. So, I can't plug in that value. Like, if I'm up here, if I'm in between, and we see both contributions are downward, so that's big. If I'm up here, the two contributions are fighting against each other, but the positive charge always wins because it's closer. And then down here, the negatively charged particle always wins because it's closer. So at a point down here, we should have a positive z component to the electric field. Let's make that. I'm going to make that the final check. So I haven't really checked things out very thoroughly here, but it is passing some common sense checks. So minus 0.02, and I'm saying we're closer to the negative charge here, which creates a positive electric field at a point on the z-axis below the origin. And so I expect an electric field in the upward direction. So plus, and it's 1.2805 times 10 to the 6. The same distance below the negatively charged particle, below the origin as I was above it. We got some symmetry there. So the last time I did that with being on the z-axis and not at the origin, I get the same exact value also upward. In either case, it's upward. I think that's cool, because upward is away from the positively charged particle, and we're closer to the positively charged particle, so it's going to win there. And then when we're down below the origin, down below the lower particle, we're closer to the negatively charged particle, which is creating an electric field upward toward it. If I put a positively charged particle at this location, it would be attracted to the negatively charged particle. So in both cases, it's upward. That's interesting for the dipole. Two charged particles at a fixed separation is called a dipole, an electric dipole. So I would say this passes the checks that I've made so far. Maybe during documentation we'll take another look at it. Well, let's take a quick look just at the code. So that's all the checks, but as far as making sure that it makes sense, the phi val, kq over r minus kq over the other r, that looks perfect. This is the norm does that. It's the x squared plus y squared plus, and in one case z minus 0.005 quantity squared, square root of all that, and that's what the norm calculates. I checked it out with the calculator for a test case. So that looks good. And then here, step is 0.001. Half of what I'm using for dx is that. The dx is the step itself. And half dx, half dy, half dz. That looks good. So here's delta phi along the x, just associated with changes in x. And then the negative of delta phi divided by the step size, which is delta x. So that looks good. So it actually is pretty straightforward. So even without building a test case and doing it out by hand, I'm confident that now that I got evec there instead of evex, that this code is calculating a good approximation to the electric field. So that does it for Project 5 Video 2.